Welcome back to the BCS Codex, episode 05, another solo podcast because, I'm still scaling, unable to find guests, and of course, I'm still arranging for setting up the studio, getting another mic. Meanwhile, I thought, there's an interesting topic this week to talk about. And this topic, it's quite important because this is considered to be a major milestone in the world of technology, and not only in terms of tech, but in AI. So, most of you must have heard about OpenAI Sora, a new text to video model that was released yesterday, I believe, and in fact, 2 days back, I think. And so, it told us about this new research paradigm that OpenAI worked upon, building on existing paradigms that they had. So, this video is all about how does OpenAI's Sora work. So, first of all, we'll start off with what is OpenAI Sora. So Sora is an AI model that can create realistic, photorealistic, and imaginative scenes from text instructions, or you could just call it a text to video AI model. Now, this is all written on the OpenAI's website, and in fact, I'm going to read you a small excerpt from the website. We're teaching AI to understand and simulate the physical world in motion with the goal of training models that help people solve problems that require real world interaction. So, key highlight on these three words: real world interaction. You see, most of the AI models that we have seen are, rising over the past few years, all of them, in fact, majority of them are based on stochasticity or probabilistic models. It all started back in 2017 with the invention of the transformer. And I'm not talking about the movie or the electric device. I'm talking about a specialized AI model, the transformer model, that introduced attention mechanism, which created this whole industry of generative AI. And ChatGPT, Google's Gemini, all the big LLMs work on that technology. But you see, these three words, real world interaction, these introduce an entirely new paradigm of AI models that we might be seeing in the coming future. 2024 is going to be splendid and a big year for AI. Later on, they continue saying, introducing Sora, our text to video model. Sora can generate videos up to a minute long while maintaining visual quality and adherence to the user's prompt. So, of course, you see, it takes high amounts of computation to create just images. Imagine how much it would require to create videos. And of course, most of the content creators who have made video on OpenAI Sora, all of them I have seen, they say that 10 months back there was this video of Will Smith eating noodles. It was a crappy video, and of course it had to be. The age was different, so they noticed that in this short span of 10 months we have achieved something so remarkable by using nothing new. I mean, there's no new technology that's been used to create Sora. It's just different configurations of existing technologies. And of course, in this podcast, I aim to explain you that as well. So it takes up to a minute long. I mean, the video's duration is a minute long. It could be less as well. And throughout the whole scene, or what we call a scene in cinematography, the scene, it changes. It has this dynamic. It has dynamics built into it, and you might have seen all the videos that are coming. I mean, it's amazing. I can't even start to share how it's done. And of course, this was limited. It had limited access to certain people. And I'm not talking about people who paid OpenAI or the investors. I'm talking about a curated list of content creators, filmmakers, designers, visual artists who who are trustworthy, who have worked on technology reviews previously. And of course, OpenAI wants to take Sora as just a stepping stone towards building a much better model, because feedback is of course needed. What problems are coming, and of course, who better to ask than the content creators who work on these things all the time. So of course, it's not limited to the public. It's not accessible to the public. It's only limited to certain individuals. Now, before I go on, like all the videos you might have seen, it has solved the problem of causality a little bit. It still has a lot of challenges. I might take this at the last. I'll take this at the last of at the end of the video. So now, for all you tech savvies who want to know how this actually works, I'll start a way of explaining the basics of technology, the basic research techniques, and then eventually we'll go through the entire technical report that was published on the website, and it's also now enlisted in the research section of OpenAI. So, in terms of research techniques, diffusion model is the number one thing that comes to play. Because you see, what is a diffusion model? If you don't know, a diffusion model is a specific AI model that uses this concept called diffusion from thermodynamics. And of course, it means that a lot of particles, if they have a semi-permeable membrane to go through, or a barrier to go through, they kind of go towards the other section of lower energy, or of lower pressure, or of lower temperature. So what diffusion does is, it starts off with random noise, static noise, the white and black. It's called white noise, the one you see on a television when you don't have a channel put on it. That's just static noise. It's random ones and zeros. And what you do in diffusion is, gradually you transform that random static noise into lesser noise. You remove noise at every step until you have reached the final output you want, which would be the generated image or the video or the audio. Could be anything. Diffusion model is of course a multimodal model, meaning it can handle various modalities of data. And what modality means is, it can handle different types of data like image, video, audio. Second big point, the one that actually has solved the major problem, is what we call model Foresight. So Sora is capable of generating entire videos all at once, or even extending generated videos to make them longer, which I'll talk about later. And how this does is by giving the model Foresight. And what that means is, it is able to understand, or rather generate, the consistency over frames of a video by having the foresight, or by knowing what of many frames at a time, what the frames information is. It has all this latent space data in a place, in consecutive frames. So that's what model foresight is. It has knowledge of what the frames are going to say in a few time frames. Also, Sora, of course, since it's a diffusion model, it uses a transformer architecture. And a transformer is nothing but, imagine it as an encoding part. It then has a latent space, sort of this meta information highway. It has all the data compressed into a lower dimensionality space, and then it decodes that. So it has an encoder-decoder architecture, or what we also call an autoencoder, and it has the special attention mechanism of a transformer. And of course, another big milestone with this is, you see, typical transformer models use what we call tokens. It's all about tokenization. You have tremendous amounts of data, and of course, you cannot represent all of that. Like, imagine millions and billions of pictures. You cannot, scale that just by creating them as numbers or encoding them. You need to create them as tokens, which are these fundamental units of an LLM. What the researchers did in Sora was to represent videos and images as collections of patches. And these patches are like tokens. They can be compared to a token. So just like a transformer uses tokens to, it's what we call tokenizing data. So it represents that data into a fundamental form, easier for the model to understand, to batch it, to process it, to help the neural network train it. In the similar case, in our Sora, OpenAI Sora, we use what are called patches, which is akin to a token in GPT models. Now, by unifying how they represent data in this model, they can train diffusion transformers on a wider range of visual data than was possible before. And one of the big advantages of this is the fact that they can allow for wider visual frames, resolutions, duration of the video. So they have all these parameters that they can play very easily with. And lastly, Sora is, of course, as I told you, it is nothing entirely new. It is built on existing research, and OpenAI had two specific models on that. GPT model, everybody knows what that is. It's a generative pre-trained transformer. It typically used in text-to-text use applications. And of course, then there's the DAL-E model, that is the image model, text-to-image generation model, and it uses what we call a recaptioning technique from DALI 3. And I'll explain this, which what it does is basically generating very highly descriptive captions for the visual training data. So it's like labeling them. There's an entire different captionizer model, which I'll talk about just for that. And as a result of that, the model is able to follow what the user's prompt is talking about. It can understand every instruction. And of course, the video fidelity, it is a high fidelity video. Now let's come to the techie part, the technical report of OpenAI. And of course, you can go through this on your own on the website, but we could discuss this here. So, I sort of have this all explained for a basic user who doesn't know about AI. The report could be overwhelming for a lot of you, but hopefully I can help you, bridge that gap. So the research on the website is titled as Video Generation Models as World Simulators. So OpenAI is all about expanding their products or their research into at much better lengths. And of course, if it would be a simple nobody without a vision, the research might have been titled Sora, a better text to video generation model. But you see the phrasing that they did: video generation models as world simulators. So it's a whole new era, a whole new area of applications. It's not just about creating funny dog or cat videos from text prompts, but it's going to world simulators. So we are talking about simulation on a bigger scale. You can simulate things. You cannot. It's not only about the content creators who would be using this product when it comes out for public access, but it would also be used by certain specialists like physics. I mean, it's not still ready for the physics part, but it can be used. It has this whole extension of applications that it can go through. And of course, Sora is capable of producing a high fidelity video of 1 minute. And of course, that's because of the computational limit. 1 minute of content with Sora if I should tell you, it's about hundreds of dollars just to do that. I mean, they're using these GPUs that cost a lot. The electricity is cost a lot. So there's tons of resources allocated to it. So that's why they put it to 1 minute. And of course, 1 minute is a good time to understand what a scene might look like. And of course, the work is focused towards building a general purpose simulators of the physical world. That's what it's all about. So our first step starts at how you turn the visual data of a video or an image, because you see a video is nothing but a sort of collection of frames, and frame is an image, a single image, a static image. That's what a frame is. You have this whole collection of frames and you get a video. So it's all about turning those into patches. And let's start off with tokens. I told you tokens are the fundamental units in LLMs. That's how data is represented. So you have all these, let's say you give ChatGPT a prompt. Now that prompt has text in it. All of that text is encoded into tokens. And these tokens are then all of them are converted into a latent space or a latent variables. And that's where all the vector space thing works. That's where all the computational thing, all the computing part is going on. So Sora has what we call visual patches, and a visual patch it's a highly scalable and effective representation for training generative models on various modalities, because text is very basic. It isn't very complex. It is about tokenizing things. And of course, NLP, natural language programming, which started off this whole thing, it also worked on the concept of tokens or the tokenization of text. So patches are needed in the case of image and video. And of course, how do you convert raw video data into patches? What you do is you reduce all of that into a lower dimensional latent space. Latent space is where, as I told you, it's a information highway, a meta information highway. It it has certain numbers. It has a collection of numbers that represent the whole data. So imagine it's like if you're able to represent the whole of our world in a single cube. You could just try to imagine that, or the whole of a world, or the best example is the entire Earth is sort of reduced into a lower dimensional globe. I mean, it's still 3D. The Earth is 3D, the globe is 3D, but that has become smaller to represent all the countries, how they look like, and the data scale is reduced. It's very easy to understand, and of course, then this latent space is then decomposed, and then you represent it, decomposing the representation into space-time patches. And I'll tell you what space-time patches are. So ultimately, what we have is this whole latent space encoding. Once you have that, now the main objective is it's all about this video compression network. You're compressing it. It's how a transformer works. You have an encoder. All of that data goes into a latent space. The dimensionality is being funneled down or reduced. So you train a network that reduces the dimension of visual data. That's what patches is all about. You have an input of raw video, and the output is space-time patches. Now, the meaning of space-time patches is that it has a spatial element to it and a temporal element to it. So spatial, we can understand. It's all about reducing the number of dimensions to our data. And what about temporally? So I remember Sora is all about creating videos from text. So it's all about, so the training of the whole model that was done at the OpenAI facilities or on a random Amazon AWS server. It's all about understanding that it's a video, and a video has frames. It has temporal dimensions to it, as in there's linearity in time. The first frame and the last frame of a video. So it all starts at 0, time t equals to 0, and let's say it's a 1 minute video, so it ends at 60 seconds. That's what the temporal part is. And this decoder model, you have the encoder model that took all the raw input as video, and it encoded that into space-time patches. Then those space-time patches is the decoder model maps generated latents back to pixel space. So it started with pixel to latent, and then it goes back from latent to pixel. That's what a decoder does. So the thing about space-time latent patches is that it allows Sora to train on media of variable resolution, duration, and aspect ratios, as I told you in the beginning of the video. Why is this done? I'll talk about that. You see, the past approaches of AI models typically focused on resizing, cropping, or trimming videos at the standard size. And of course, this was a classic old thing. You need to be specific, and fidelity needs to be maintained. So you crop out a video, or you resize it just to reduce the dimension as much as you can on your end. But the research on Sora found that it's better to train the data, all the video data, on its native size. And why is that? And when I say native size, it's what I mean is, so you have a video that's a landscape video, you have a video that's a square video, or you have another video that's a vertical 9:16 video. So it's a vertical landscape, say a TikTok reel or whatever. Now, don't resize, don't crop anything, don't standardize all the data, normalize the data into a specific defined set of numbers. But what you do is train it on the native size. There are two reasons for this. First is sampling flexibility. So all the screen layouts, because you need to cover all screen layouts in such a project, because it's not just LCD, it's not just cathode CRT monitors now, just the square layouts. We have a multitude of device sizes of different aspect ratios. So you need to create content for native aspect ratios of a native device. And of course, the sampling flexibility also ensures that when you want to create a lower to full resolution transition, it becomes easy, right? And the second reason is improved framing and composition. So typically in the Gen AI field, what people do while they're training videos is they crop the videos into square. As you might have seen in the beginning of text to image models, usually the output was in the form of 4 squares. It's very typical. And the reason was the same thing. It was able to crop certain thing, and square it's a well defined structure to show the results. So it stuck in the industry, and what they were doing was that only. But typical gen models do that. But the problem in this is that the object of interest, let's say it's like the prompt they had on the website. There's a diver, and because of the square layout, his half of his face, half of his body is hidden. It's partially viewed. Training the video on its native size, on its original size, ensures that the object of interest isn't hidden. It is not partially viewed. You can view it fully. So it's better that way. And of course, since it's a transformer, it requires NLP techniques. It also uses recaptioning technique from DALI 3, which I told you is training a highly descriptive captionizer model, or sorry, a captioner model, to produce captions for all our videos in our training data set. It gives it labels. So in a way, it is a semi-supervised machine learning method. It is creating labels, and once it has done those created those captions or labels, it then uses that to train all the other videos of similar videos. And of course, this improves text fidelity and overall quality of videos, because you have a label now, and you connected the video with that label, with that caption. And and one more amazing thing, they use GPT. They leverage the power of GPT to turn short user prompts into longer detailed captions. And of course, humans are lazy. That's a basic fundamental psychology, a psyche of our mind. We are lazy in prompting. I mean, whenever you might have tried using a text to text model or a text to image model, you still have some sort of this missing element where you can't ultimately or fully explain what it's all about. Your prompts are not clear and not well defined. So GPT helps you with that, and then that input goes to the training part. So they're using fundamentally three technologies. They're using DALI, they're using GPT, they're also using, as I told you, patching and model Foresight. Now, all the examples on the website are text to video samples, but Sora can also be prompted with other media types. When I say that, I mean image and video. So in that way, it becomes a multimodal AI model. It's not only text to video, it's image to video as well, and it's video to video as well. So that's amazing. And with that, since it's an image and video input model, it can perform all these varieties of tasks on it. You can loop a video, you can animate static images into videos, you can extend the video forwards or backwards in time. There's tons of things to do. And of course, there's also this whole concept of a car driving in a forest. You can change the style of the background, the environment around the object, and it's all zero shot learning. It's done in that way. So that's pretty amazing. And of course, it can also incur seamless transition between two input videos with different subjects and scene compositions. So it's like a drone flying through the Colosseum, and you want to turn it into a butterfly sort of swimming or flying in an ocean. It can do that seamlessly. So that's pretty amazing. Sora also generates images, by the way, because you see, ultimately videos are frames or images. So it does it. The fundamental thing is to generate images, and then using model Foresight and patches, it becomes a video. So patches of Gaussian noise in a spatial grid with a temporal extent of one frame, which is an image. That's what's used to do that. And it can hold up to 2K resolution, or 2048 by 2048. And the most important part of this podcast, how does this whole process transition or emerge into simulation capabilities? As OpenAI has said, they're focusing on the future, and simulation is a big part of it, not only in scientific work, but just as part of pop culture, which defines our race. So a few things they mention in the technical report. First is what they call 3D consistency. And you see in the videos that whenever there's this dynamic camera motion, a camera going in or going out, it's the objects around the object of interest are able to modify themselves, elongate or contract in terms of how the camera moves. That's not something you usually see in video text to video models. It's something very hard to achieve. I mean, in game environments, everything's about vector algebra. It's all about eigenvectors, contracting them, extending them when the camera moves. And it's a real world simulation, but in a stochastic process, in a probability field based process, it's almost hard to do. And they were able to do this with Sora. And of course, another great thing is what we call long range coherence and object permanence. So one of the biggest problems that have been in T2V models or text to video models is the problem of temporal inconsistency. And with model, what that means is as time progresses in a video, as frames progress, it's very inconsistent to what's happening in the first few frames and then what happens in the next few frames. It's inconsistent, it's incoherent. That still stays a bit of a problem, but I mean, a lot of that has been solved in Sora with model Foresight, of course. And one of the best things I saw, Sora can simulate actions that affect state of the world. Imagine that. So it understands how, to some extent, it understands that certain actions create or change certain states of the world. So it's like you spill a glass of water let's say in Sora, a glass of water is spilled. It's able to capture that spilling, that fluidity of the water to some extent. I mean, there still are problems, but it's much better than what happened 10 months back with the whole Will Smith eating noodles thing. It is a massive change. And personally, what I find the best is a use case. They have implemented this Minecraft thing in Sora, and what it does, it simulates digital worlds. But not only that, Sora can control the player in Minecraft with a basic policy. Policy is part of reinforcement learning, which is nothing but a special function that maps out state to action. So you give it a state, and it is able to sample an action for the RL agent to do. And it uses this policy while also rendering the whole world in Minecraft and all the dynamics in high fidelity. All you need to do once you have the model is zero shot all of it by prompting Sora with the caption having the word or mentioning the word Minecraft. If you use Minecraft in your prompt, it understands, okay, it's a special prompt. It's going to actually play Minecraft in front of you in a simulated environment. Just imagine that. It's mind-blowing. I'm still going nuts over this. Now, to end this video, as I told you, there are some challenges that need to be tackled. These were also on the overview of the website. Let's start off with that. So it may struggle with accurately simulating the physics of a complex scene. The physics part is still needs to be improved a lot. Since it's a stochastic process, randomness is all part of it. How much you refine, at some extent, it doesn't matter. Ultimately, it's randomness. Physics is not about randomness. Physics is deterministic. There are certain processes that happen that are defined that way, and it still isn't able to understand. It may not understand specific instances of cause and effect that we see. So there's this example: a person might take a bite out of a cookie, but afterward the cookie may not have a bite mark. But in another case, we did see a person eating a burger, but that burger had a bite mark. So sometimes it fails in that manner. And of course, it also confuses in spatial details of a prompt. For example, often mixing up left and right. It's not able to understand the directional logic of that. Also, it may struggle with precise description of events that take place over time, like following a specific camera trajectory, how the objects react to it, all of that. It still misses a big thing in object-to-object interactions and relationships. So, as I told you about my previous research, neurosymbolic AI, where it utilizes a symbolic AI to understand how real-world objects behave and how their relationships to other objects become. It still isn't good with that. And of course, it doesn't work on well-defined predicate logic. That's what it's all about, the symbolic part. It's a stochastic model at its core. And finally, the final point is there is incoherence in long duration samples. So often in videos, you see that there's this continuation or consistency of frames, but it still has this challenge of not getting that ultimately. Also, there's spontaneous appearance of random objects in a video that were not meant to be there. That's still a big challenge for them. So this was all about the technical report of OpenAI Sora. How do I see the future of Sora? I do believe with enough computational power, more training data, and if they get a way to handle all the causality things, I would love it. I would love to be part of a research where they include neurosymbolic AI, or at least concepts from it, to help Sora develop much better to understand causality, real world object interactions. I would love that. But hands down, it has been one of the best product releases, or a concept releases I've ever seen. More than so than some Apple products as well. This is game changing. It's mind blowing. And once it goes into public release, once it has this public release, we are seeing all kinds of content creation. I mean, it's mostly going to be used for content creation. There's hardly going to be a few good concepts that people are going to show on, let's say, Twitter or somewhere. But I do hope for it, and I hope it becomes a better thing in the future. So that's it for now. Hope you like this episode of BCS Codex. Next week, let's go for something non-technical. There's 3 episodes of tech as of now. So if you know of a good topic going around the world that affects our species in some way or the other, let me know and I'll cover that. Signing off for now. Have a good day.